This is video 20 in the demo course with Lars-Erik. This one is about the number of equations in a PT flash calculation. A PT flash is here defined as a feed where the mole fractions are defined as sex. Then it goes into a tank where we get some vapor, some liquid. The liquid composition are the x's, and the vapor compositions are the y's. And in a PT flash, we assume that the temperature and the pressure are known. And then the question is about number of equations. Then I will first list up the equations available. We have mesh, short for material balances, equilibrium equations, summation equations, and enthalpy or energy equation. We have material balances for the total and for each component. We have equilibrium and that might be defined by a k value, which is y over x. We have the summation equations of fractions, which should be 1.0. The sum of mole fractions in the liquid should sum up to 1, and the sum of mole fractions in the vapor should sum up to 1. And there might be an enthalpy or an energy balance. In case of a binary system, an ideal gas and ideal liquid, we start with the number of unknowns. In this system, we have the vapor, the liquid, the x1, x2, y1, and y2. In this system, we know the feed, we know the temperature and the pressure, but we do not know the vapor flow, the vapor composition, the liquid or the liquid composition. So we can state that we have 6 amounts. And then we have the equations. And we can state that H is not relevant. We have a constant temperature. Then we have the material. Balance, and let us start with the total, which can be said that the feed should equal the vapor flow plus the liquid flow. Actually, we have to assume a steady state. We assume that there is no time development here. And then we also have component 1 equation, which states that the Z1 times F equals Y1 of times V plus X1 times L. And then the material balance for component 2 is not independent. So the number of equations is 1 here, and it is 1 here. We are counting independent equations. And then we have the equilibrium, and when it is ideal, then Ki, we do not need to define the case here. We only need to state that the ratio between Y and X is the saturation pressure over the pressure. And then, because we assume here ideal gas and ideal liquid, and then the ratio of the Y and the X is the Isaac over P, and then we have 2 equations. And then we have the equations that are easy to forget, and that is the summation equation, which state that the sum of x's is 1 and the sum of y's are 1. And then we have the total number of equations is 6. And then we have 6 unknowns, and we have 6 number of equations. Then I go on and I now say that we still have a 2-component system. With the assumption that we have the equilibrium described in this way. Then that is another way to state that we can have non-ideality in the gas described with a fluidity coefficient, and we can have a non-ideality in the liquid defined by an activity coefficient. And the fluidity coefficient can be calculated as a function of pressure, temperature, and the vapor composition. And the activity coefficients can be calculated as a function of temperature and the liquid compositions. Then, to get an overview, I try to find the number of unknowns. And we have the same as we had in the ideal system. V, L, X1, X2, Y1, Y2, but we have 2 more unknowns, and we have it for both components. So we can add the fugacity coefficient for component 1 and 2, and the activity coefficient for component 1 and 2 as unknowns. And that adds up to 10. And now 10 unknowns that is so many that we have to, we will lose the overview, so we have to have some system of systemizing this. And we then start with the material balances, and that is still valid. And set 1 F equals Y1V plus X1L is still valid. We have that is 1. That is 1. We can not put up another one for component 2, or we can do that, but it will not be independent, I try to calculate or to find the number of independent equations. Then we have the equilibrium equations, and then we have the functions for the piece. That is 2 for gamma. That is 2. Those 2. And that is 4. And we have this definition equation of the equilibrium for this case. So we have Pi times Yi times P equals the activity coefficient times the xy times Pi z, which are also 2 equations, one for each component. And then we have 10 unknowns and so far 8 equations. So then we must have forgot something, and that is very often the summation equations, which are still the sum of x's is 1 and the sum of y's is 1. Then we have 2 equations, and that gives a total of 10 equations. And then we have 10 unknowns, and we have 10 independent equations to calculate that. So the idea is that we have an example of a calculation, in this case a PT flash, and first we have the ideal case, and then we have 6 unknowns, and we have 6 equations taken from these mesh equations, which are independent, so that we can solve the problem. If we may take the non-ideal example defined by this equation, introducing fugacity coefficients and activity coefficients that we don't know, then we have the same equations as in the ideal case, but we have functions, these functions for the fugacity coefficients and for the activity coefficients. Those are 4 functions, and we define the equilibrium by these equations. In the non-ideal case, we defined it by these equations for the ideal case, and we also have 2 independent summation equations, and that adds up to 10. So this is the end of video 20.